Hello, welcome everyone. Good evening. Welcome back for another virtual science camp. This one's on phase changes in the kitchen. So hopefully most of you gathered the recommended materials I suggest you have for this one. Also, just a heads up before we get started, like often I remind you, it's best to switch things into speaker view so you can see me or my guest host spotlight. So if you forgot how to do that or don't know, the view is up in the top right. Go to view and just switch it to speaker view if you want to see us nice and big rather than seeing everyone in the gallery view. So this, like I had said before, is following up from Tuesday's science show that about half of you were present for, where we were looking at, well, the science show was called It's Just a Phase, and then went over some phase changes, liquid to gas, solid to liquid. I don't think sublimation was covered. To explain how a cloud chamber worked, with Anja finally getting it to work in the end. Here we'll have some experiments to do on your own at home. The first one, I have a special guest host. This is a student from my school. He won my science video contest back in 2017 with an experiment on instant ice. So he's here to demonstrate this one. This one, I didn't recommend you prepare materials for. It's something you can definitely redo afterwards, but because it's a little bit finicky on the setup, it takes a couple hours for the bottle to freeze. I felt it's best to show you live in the session rather than try and give you instructions on how you do it live with us. So this one is just to watch for now, but hopefully most of you guys will try it at home afterwards. I'm just going to spotlight Jose's video. So Jose, the floor is yours. Turning things over to you.
Thank you very much. Yes, this experiment is actually it's very easy for everyone to do. You just need it really the timing is really key for it to work. But so my name is Jose, and I'm at the school from Mr. Gregory, so École Jean Manuel, and right now I'm 16 years old. But 3 years ago, I when I participated in the contest, I did an experiment on instant ice. So it consists in I around 2.5 hours ago, I put a bottle in the freezer right now, and my objective is to get it to be to reach like its coldest point before freezing, yet still not becoming solid. And with that water, we can do really fun things like any movement or anything that interrupts the I don't know. So anything will make it freeze instantly, and it's a really cool thing. So I'm gonna go get the water bottle right now. Um, so yeah, it's been around 3.5 hours. It really depends really depends on the freezer you have, but so it might take a little longer, a little less time. But yeah, so what I'm gonna do is I'm gonna pour it into this glass here. As you can see, it's still very liquid, and I'm gonna add like a little ice cube that I have here. And hopefully it will instantly freeze. No. So right now, the the water, like, actually, I don't know if you can see in the camera, but crystals are forming, yet they are very little, and that's because I didn't put it enough time in the freezer. I did this a little while ago, and if I can share my screen, uh, I did this a little while ago, and it actually worked. So I'm gonna play the video right here. So this was like 4 hours ago, and it worked. So that's what's supposed to happen. The moment you introduce the ice cube, it's supposed to freeze completely, and then you can do things like this. It it instantly becomes like a slushy, and it's really fun, and it's really easy to do, and it's amazing when you actually get it to work. So so I really recommend. So yeah, I recommend doing this experiment because it's really cool. Now how it works is that when the water reaches the such a cooling point, little tiny crystals of the water are in sorry, little tiny crystals of ice are inside the water, and but they're not visible without like a microscope or anything. So and when you introduce an element like an outside force, for example, if I bang the bottle really hard, the water bottle would freeze too. But so by introducing any external force, the cooling process of these crystals were will speed up, or and they will crystallize a lot faster, and thus the water will completely freeze in a few seconds. So yeah, it's a really amazing experiment that well, I had a lot of fun. I had a lot of fun with a few years ago, and now too. I had fun this morning while I was preparing it. So that's basically the experiment. I really recommend you attempt it at home.
That's excellent. Thanks for sharing that again. And just a couple of words of encouragement for anyone trying it at home. As you saw, Jose, who's done it a number of times before, I don't even know how many times you must have done it when making your video. Do you remember? Was it like probably well into the tens, right?
Yes, it was. It had taken a long time, and actually, in my video, my reaction was very genuine because I was very annoyed that it wasn't working, and it worked. That when it worked, I was really happy.
That's amazing. And I remember how much enthusiasm came through on that. And I'll just share my screen for a second to show everyone the video contest. So this is his video that won the video contest a number of years ago, how to make instant ice. And I think his first reaction for that is about a minute and a half into it. So the reaction he's talking about is just here.
It's freezing. Oh my god! It's frozen and it's freezing. Look at that. It's.
And so don't worry if the first time it doesn't work.
Do it again. Do it again. Put the video again. I didn't really see it.
Oh, well, I'll share the link with you guys to the video in the chat. And then if you're interested, I recommend watching the whole video, especially for troubleshooting, trying to do it at home. So I'll just add that in the chat once I find the chat again. And here's a link. So I'd recommend wait till after so that you're focused on the experiments you're doing with me at the moment, and then go back and watch it afterwards. But if it doesn't work the first time, it's probably either if you come out with the bottle and it's frozen solid, or if it doesn't solidify, in which case it just needs a bit more time. So if you have a lot of room in your freezer and a lot of time to try it, a good thing to would be to put 3, 4, 5, 6, 7 bottles in the freezer at the same time. And after about 2.5 hours, take one out, try it. If it's not enough, put it back. But you can take another one 15 minutes later, another one 15 minutes later, and you'll kind of find the time that suits your freezer.
Yeah, I think the right time that, well, roughly the right time is 3 hours. You should leave it 3 hours at least in the fridge, in the freezer, sorry. And I think, well, it you can try to give the bottle as much space in the freezer as possible. And like don't like clump all the bottles together. It really needs like space, otherwise it will freeze more easily inside the freezer.
And of course, if you have several bottles right next to it, then it'll increase the amount of time because there's more heat to get out of them to cool them. And there was a question if it's pure water. Yeah, the easiest is if you have water that like you haven't done anything with. Tap water, if you're in Paris or another place with hard water, there's a fair bit of dissolved carbonate, which will make it so it might not have as strong an effect. Like it definitely can work with tap water, but probably while you were using bottled water, like Evian in that case, that's a very mineral poor one, so the dissolved content will be fairly low. So if you're trying it, if you want to try it with tap water, it'll work a lot of the time, but it'll work more consistently if you have water with even less dissolved salts. Excellent. Thanks again for sharing that. Now we'll move on to some of the experiments that participants are hopefully going to do at home. So,
Thank you very much.
Oh, well, thank you again. Okay, so the first experiment I'm going to ask you guys. Oh, actually, one small other one that I'm going to show, kind of related to instant ice, and I thought of it because it looks very similar. I'm going to show you guys something called hot ice, and this was one I was thinking of recommending to you guys after the balancing chemical equations in the kitchen, because we mixed a lot of vinegar and baking soda. And if you take vinegar and baking soda and then you boil it to evaporate all the water, you're left with something that'll either be clear or yellowish color if you lost patience and you heated it at a high temperature. And this is sodium acetate, which is also known as hot ice. And you can see it's a liquid here sloshing around, but it's actually a supersaturated solution. And if I introduce it to some crystals, so similar thing, in this bowl, I just have some sodium acetate crystals, and I'm going to pour it onto here. Just kind of position this so it's a little bit closer, not too close so I don't spill too much. Then we should see it crystallizing quickly. Somewhat underwhelming there. That's not quite as quick as it was supposed to be. Maybe it's still warm because I heated it just before the session because I accidentally solidified it. Let's try with this other one. Well, that's a way to start things off with an underwhelming reaction. I'm going to put those in the fridge and I'll show you at the end of the session, and hopefully it'll be amazing at the end. But then the next experiment we're going to do is with a candle. So please get a candle ready. If you're young enough that you shouldn't be lighting a candle on your own, please get an adult ready to light your candle for you. Okay, so here let's take one without so much wax. Okay, here I have a candle that I'm about to light. An interesting thing about candles when we look at phase changes is only wax vapor can burn. So if I try and burn the solid wax without lighting the wick, I can put the flame to it all I want, and that part's not going to burn. When I light the wick, it burns, because what's happening there is the wax is being heated up near the hot end of the flame, and you can see this closer if you're looking at a candle yourself rather than looking at my candle. But the tip of the wick is usually glowing very faintly red, and it's so hot that it's causing liquid wax to evaporate, and it's the wax vapor in the flame that's actually on fire. And we can test this and demonstrate it in a couple of ways. So what I'm going to do first, I'm going to grab another match and keep it handy. This works as well with a lighter, or if you have a second candle, like if you're not using matches, you can do it, just your hand might be a little bit closer. And I'm going to blow the candle out, and right away I'm going to bring the other flame next to it. And if you look close, you can see the other flame doesn't have to touch the wick itself. It'll light from about 1/2 centimeter away, because the wax vapor is still evaporating and it'll travel upwards from the wick into the air. So as long as it's fairly quick again, you'll see the flame traveling down through about 1 centimeter of air back to the flame. And again, if we want to demonstrate that liquid wax can't burn, because I'm saying that only wax in a gas form can burn, I'll just get another match lit, and I'm going to take a candle I've been burning for a while, so there's a lot of liquid wax in here. And same the liquid wax, if I don't have a wick, I can touch the flame to it, but the liquid won't stay lit. And that's useful to know if you want to design candles or if you want to make your own candle. So I'm going to show you another demonstration. I'm going to suggest don't do this one because I didn't suggest that you have vegetable oil handy. But if you want to do this one afterwards as a follow-up, you can always do that. So I'm going to just take a little bit of paper towel, and this is a homemade candle that I came up for when I was a kid at summer camp in Canada. Because all the counselors, they had candles to keep their cabin lit at night. And I wanted to play cards with my friends, and we just had flashlights. And with flashlights, the light goes in one direction rather than lighting up the room like a candle. And I was a kid, I was at camp, I couldn't go into town to buy a candle, and the staff wouldn't give me a candle because it was their candles, and I don't think they wanted kids having candles. So I thought, well, I don't need a candle. I can just get vegetable oil or margarine at breakfast that they gave to put on bread, and I can make my own candle with that in a napkin. So I took a bit of napkin. Here, this is a bit of paper towel, and just a small bit so it makes a wick. And same thing, I'm going to demonstrate like I did with the candle. I'm going to put some vegetable oil on this plate. It's probably a lot more than I need. And at first, without the wick, I'm going to try and light it on fire. And even though it's flammable, it's only the vapor that's flammable, so you can see this isn't lighting on fire. However, once I introduce the wick, and just like in the candle, the wick will heat up and we'll have oil vapor which can burn. If I manage to get the match lit. And that wick is drowning a little bit. I just need to bring it a little bit more out of the oil. And it's not a candle, so it takes a little bit more heat to light to get the wax vaporizing. And now we have that lit, and it's not the paper that's burning, it's just the wax, and the wax in vapor form. So if I leave that, that can stay lit until it burns the whole puddle of oil. And so I'm just going to put it near the middle of the oil, if it doesn't drown out the flame. I'm going to reposition it, and I'm going to relight it, and hopefully it'll stay lit in the background for the rest of the session. And this homemade candle is also really handy. I don't know how many of you have or will end up spending your 20s living in Paris, but if you're in your 20s and you're in Paris and it's someone's birthday, people are almost always think of a cake, but only when they go to give the cake to someone will they think of candles. And most birthday parties you might end up at, there'll be a cake but no candles. So if you know how to make your own candles, you can make someone's birthday just a little bit happier. So remember the science of phase changes, and that most oils and petroleum products, only the gas stage will burn. So that's the candle one. Does anyone have any questions on that one before we move on to a couple of colder experiments?
So I have a question about the courses. Yeah,
of course. If it's a long one, I'll leave it for the end, but if it's a one I can answer quickly, I'll answer it now.
Oh, no. I saw on the Google Forms, I saw this course and another one on Tuesday. Are there any other courses that we can join?
Yes, thanks for that question. So I'll be sending out the schedule probably tomorrow. There have been a couple of changes, and the guest host for next Saturday canceled just this morning or yesterday. So I'm rearranging things a little bit. But yes, on Tuesdays and Saturdays still until the middle of February. Then there's this school vacation here in Paris. I'm probably going to take a break then and then start back in March. So as long as you signed up for this or you're on the mailing list, you'll get a schedule of the upcoming sessions, probably tomorrow. If I don't get to it tomorrow, it'll be like Monday morning or so. And if anyone's interested at the end of this session, I can stay on for a couple minutes and overview a couple of the things and give you some heads up of the suggested materials for upcoming sessions. And it turns out my candle went out, so this model of candle isn't that great, but I mean, that's little kid me inventing a candle, not the best candle in the world. Okay, for the next experiment, we'll want some hot water in a couple minutes. So it'd be a good idea to put on a kettle of water now so that you have hot water in a couple minutes, and get some ice cubes handy. So I'm just gonna turn on my kettle and grab some ice cubes, and I'll be back here in just a second.
Mr. Gregory?
Yeah, what's up?
Can we put our candle off?
Oh, yeah, sorry, I didn't mention we're done with candles. You can turn your candle off, yeah, or like blow it out. That's a great question, yes. So unless you have a reason to keep a candle lit, please blow out your candles. Okay, and I'll just wait another 30 seconds or so in case people are still grabbing ice or putting a kettle on. Let me know if you have any questions for the time we're waiting to make sure everyone's ready for the next experiment. Okay, and it looks like everyone I can see with the cameras on is back, so I'm going to assume that everyone's ready to go with the next experiment. This one is one where you'll need a glass, or in my case, because I want it to be big so that it shows up well on my camera, I have a clear bowl. But I originally tested this out with a glass, so don't think that you don't have the right material as if like mine looks bigger than yours. I'll do it with both, but I'll focus the camera on the bowl so it's bigger. And what we're going to look at is a freezing solution. And this is pretty relevant today because anyone who's in Paris like I am saw that we had a couple of nice phase changes with the snow on the streets today. So I'm going to take a couple of ice cubes. Again, mine are probably bigger than yours, but I have really big ice cube trays. I have smaller ones too, but for demonstration, it's handy having really big ones. This works perfectly fine, if not better, with smaller ones. But smaller ones don't show up as well on camera. Okay, so I have some ice, and I've got a thermometer here, and I'm going to try and measure the temperature of the ice. Now, the ice is solid, so that's not going to work so well. Like I can see my thermometer is going down, and that probably doesn't show up very well on the camera. But because the thermometer is not going into the ice, it's only measuring the surface, the temperature at the surface of the ice and of the air surrounding it. So I'm going to add a little bit of water, but I'm going to leave enough space that we have some ice above the surface of the water that we can look at in a minute. And I'm going to put the thermometer in the water. And not surprising, we should come up with a very familiar temperature once things come to equilibrium, like once the ice has cooled the water. What temperature should this be at? Can anyone yell out or write in the chat what temperature water should freeze and melt at, or like an ice and water solution should come to? Anyone just turn on your microphone. It's hard to see your cameras when I've moved my my screen down to focus on this. Okay, and oh, in the chat we have 0 degrees. Perfect. And for some reason my thermometer is reading 9.2. So I definitely have a problem with my thermometer. I trust more the physical effect. Oh yeah, and my thermometer wasn't in the water. Hopefully for you guys at home, it should be reading 0 as well. The next part, we're going to add some salt to it. And are there any predictions the effect that the salt will have on the temperature? Either write in the chat or shout out with your microphone. What will adding salt do to the temperature of the ice? Okay, so in the chat we have Alex saying it'll heat it. The other two options are it could cool it or it could keep it exactly the same temperature. Okay, and we have it will make it colder. So we have divided opinions here. Let's test it out. The best answer to any question is an experiment.
How much salt do we put?
A bunch. So if you feel the need to measure, then you can use a spoon, like I'll show you with a spoon, but I almost never measure when I do this. And I'm going to put about 5 spoons of salt. If you don't have a lot of salt in your house, like if you're low on salt, you don't need to put as much. This isn't an exact thing at all. It's some amount between some and a lot. So I think that was about 5 spoons, but they were kind of overflowing. And it starts to melt the ice. And you know that if you're somewhere cold and they put salt on the roads to try and melt the ice. And we're looking at the temperature. Does anyone have any results yet? Did the temperature go up, down, or stay the same? I see a bunch of people eagerly measuring temperature. Oh, dropped my thermometer in the liquid again. I see a bunch of people measuring. Can anyone tell us what temperature their thermometer is reading now? Oh, it went down. Okay, minus 1.2. So that's definitely colder than 0. Mine's at minus 0.6 and getting colder. And I'm just going to stir it around to make sure things are like mixed up well. And it turns out that if we have enough salt and we get it getting as cold as it possibly can with this method, we should be able to get it all the way down to minus 18. It's rare to get it actually that cold. It's fairly easy to get it down to like minus 10 or so. Does anyone want to try and explore? Oh, okay, we have someone who's at minus 10 already, another minus 3.9. Okay, so it is getting cold for a lot of people. And usually we'll get it only to about minus 10 because there's always heat from the outside that's going to be coming in. So if the temperature gets colder, how come the ice is melting? Can anyone suggest an explanation for this?
Well, maybe the ice melts. The salt melts the ice.
The salt melts the ice. Excellent. So we have the salt that's melting, but the salt's not heating up the ice. So all we're getting is the phase change. It's going from solid to liquid. And some of you probably know about the arrangement of particles in solids and liquids. In liquids, particles are moving more freely. They're kind of moving around. So we're giving them freedom of motion, and they're moving more. So they have more kinetic energy there. But the energy hasn't come from anywhere else. So taking them out of the solid structure where they're fixed in place, and that's what the salt does, it rips them out of the solid structure. They don't have the energy to start moving. So they actually drop their kinetic energy. Temperature is a fancy way of saying the average kinetic energy of the particles. And so the temperature drops to compensate for the change of state. If we think back, okay, minus 57? Minus 57 sounds excessive. I think the thermometer's probably doing something wrong. Some, if they're not meant to go to very cold ranges, they might get an error and read like an arbitrarily low value. But I think I saw someone get minus 17, which sounds great. And this freezing solution, if there's anyone who either is in the US or grew up there, or Liberia, because those are the two places that still use the Fahrenheit scale of temperature, you might be familiar with minus 18 Celsius. That in Fahrenheit is 0. And Fahrenheit, when he was developing his temperature scale, he used this. The coldest temperature you could easily get in the lab in the 1700s was by mixing salt with ice. And you could get down to minus 18. And that was the 0 on the Fahrenheit scale. What he chose for 100 was body temperature. Now, again, if anyone grew up or is in the US or Liberia, you might know that body temperature is closer to 98.6 Fahrenheit. We're not sure if Fahrenheit either usually had a fever or if his instruments were just off by 1.4 degrees, but that's where that scale came from. Okay, moving on to the last demonstration. Kind of like 1.5 demonstrations, actually. So the hot water from the kettle, I want you to grab the empty plastic bottle. Mine has some water in it from something I previously demonstrated, so I'm just going to pour that out. And you're going to carefully, and again, for those of you who are younger, I'm going to suggest you get an adult to do this. I want you to fill it with hot water. Now, the water from the kettle might be slightly too hot, so I'll suggest add a little bit of cold water from the tap to the kettle water so that you bring the temperature down to about 80 degrees. If you have a thermometer handy, you can measure it, but just like a little bit of cooler water should be enough. And the reason for that is both so you don't burn yourself and so you don't melt the bottle. You'll see my bottle's kind of deformed because I melted it with water that was too hot. Again, I'm going to carefully add about 2 or 3 centimeters of water into the bottom of the bottle. So just so there's some water. Again, it's not a precise amount. It's about 2 or 3 fingers height. And it's hot enough that we have steam in the bottle. And I'm going to do one more thing before the bottle's ready for the experiment. And I'm going to light a match. And again, if you don't have matches, if you were using a lighter to light your candle, you could burn a little bit of paper, you could burn the candle, but something so that you have a little bit of smoke. You'll see when I blow the match out, and this should be a familiar phenomenon, we'll have a little bit of whitish gray smoke that comes. And I want to put that inside the bottle. And the reason for that is we're going to try and make a small cloud in a bottle. And for the water vapor to condense, it needs some small particles in the air to act as nucleation sites. That's where the water can condense. Now, if you're in Tuesday's session, in It's Just a Phase, you'll remember Anja making a cloud in a bottle using like a spray bottle keyboard cleaner to pressurize it. Very similar thing, only we're going to use our hands to pressurize it here. So shake up the bottle so that there's plenty of water vapor. You'll notice if it hasn't condensed, it's perfectly clear. And then I'm going to squeeze the bottle as hard as I can, and I'm going to let it go. And for about half a second, so you need to be quick to see it, half a second, you'll see it clouds up, and then it goes away. And you can repeat that as many times as you want. I'm going to hold a white paper behind it so it turns up a little bit better on camera, but it's always best if you're seeing this at home. So white paper behind it. So just during the decompression phase, again, half a second to a second, we have water condense into a cloud. And that's from the change in pressure, because the condensation point of water, the boiling point of water, gets lower at lower pressures. So it'll be a saturated, the air will be saturated with water vapor at normal pressure. We squeeze it, that can cause more water vapor to fit into the air, and then lowering the pressure, it comes out of solution. Okay, the last demo to finish it off, we're going to combine these two things. So a little bit of hot water in the bottom of a glass. Oh, this works best if the glasses can fit into each other. Or in my case, yeah, if the glasses can fit into each other. And I'm going to take some of the salt water solution. Actually, I'll only do the big version, but you can do a small version with cups at home.
How much do you have to put of water?
Again, about 2 or 3 fingers. So it's not a very scientific measure, but some. Okay, the big version of this, we'll use this jar. Okay, so about 2 or 3 fingers of hot water in the bottom of the jar, and we can see steam flowing out of this. When we can see steam, it's actually already condensed onto dust particles in the air, because when it's just in the vapor phase, we can't see it at all. And like I did with the bottle, I'm going to add a little bit of smoke just to serve as a nucleation site. And it shouldn't appear cloudy with smoke. I'm not very impressed with these matches. So just filling the jar with some smoke. And then I'm going to put some of the freezing solution on top. And what we'll have here is 3 phases of water all in one demo. At the bottom, we have water that's hot, about 80 degrees, something hot enough to give vapor. In the jar, we're going to have a vapor phase of water. And one of the first things it does is it condenses on the side of the jar. If you touch the side of the jar, you'll notice it'll be warm to the touch. As it heats up more, we'll get less condensation on the outside, and we'll be able to see the inside of the jar. And at top, we have ice and the freezing solution. If your ice cubes have all melted, just add another if you have another one handy, because we want to keep the top about 0, or if we got it down to -18, -18 is even better for this demo. And we can see as the condensation starts disappearing from the side, we'll be able to see inside. And inside, it's actually going to be cloudy, and we'll see the clouds falling down from the top to the bottom, because the water vapor rises from the bottom to the top, cools at the top, condenses on the nucleation sites of the smoke, and falls down as a cloud or vapor down to the bottom. So this is a second variant of a cloud in a jar or cloud in a bottle demonstration. I'll just leave that there to keep going. and it'll become even more clear as the condensation goes out of the way. That was the last demonstration I wanted to finish off with, and I realize I've gone a couple minutes over time. So I'm going to wrap things up there, but I'll stick around. I'm happy to answer any questions people have, ideas how they can keep doing these experiments at home, or if you have more questions about the next sessions coming up after the questions, I'll briefly go over the upcoming sessions if anyone's interested. But for anyone who doesn't have questions, this is going to leave. Thank you for joining me for these experiments. I hope you learned something and had fun, and have a great rest of the evening. And does anyone have any questions? Oh, and thanks, Marco. Have a great evening too. Okay, Alex, yours is looking good, although I'm not seeing the cloud vapor coming down. It could be it's just not coming up on camera. Is it working okay for you?
I'm not seeing it as much. I can see a tiny bit of it though.
And the vapor coming down like that, I don't know if those of you who were here on Tuesday saw well into Anja's cloud chamber, because cloud chambers are kind of finicky to like look at well, but that falling vapor is exactly what you end up looking for in a cloud chamber. And it's through like particle traces that you'll get like a darker thing within that mist that's falling.
It's not working. Our thing is not. There's no like smoke. Go ahead.
Okay. Did you have a match or something to add a little bit of smoke to the jar or the cup?
You can see it. Well, we can't really see the smoke.
Oh yeah. Here.
You can see the smoke coming down. Yeah. There's not a lot of smoke, but there's
Like
just a little bit.
Yeah.
And if
you have to burn the match for a long time.
No, not for very long. And like, it's not actually the smoke of the match that you're going to see. Like if you waited for things to cool down so the water wasn't vaporizing anymore, you probably wouldn't see anything in there. But it's the water vapor collecting on the smoke from the match.
Oh yeah, you can see it now.
If you wanted to get even more visible, you could use water that's even hotter. Like for safety, I recommended you add some colder water to the kettle, but like the bigger temperature difference possible, the more visible this will be.
It's working better this time. I see the cloud now.
Oh, perfect. Did you use hotter water?
No, I used well, this time I tried with a candle last time to put the smoke in, and it didn't work as well. And I've tried with a match this time, and it works better.
Oh, okay. Yeah, the smoke from a candle will have a lot of like wax or longer chain hydrocarbons, like not really long, whereas from a wooden match or from paper, it'll tend to be shorter, like a couple of carbons in them, and they'll make smaller particles. So you'll have more of them, and they'll make better nucleation sites. And the bigger the temperature difference you get, and also the bigger the height difference, because you're looking at a gradient in temperatures. And so it would be wildly impractical to ask everyone to have jars that are like 20 or 30 centimeters high. But if you were doing this in a lab setup, you could do it with an aquarium or a measuring cylinder, so you have a bigger height difference. And in the case of doing it so that you have like a lot of cloud vapor falling down to make a cloud chamber, then it works well if you could get things really cold. Like Anja was using liquid nitrogen, which is minus 190 something degrees. So like a 200 degree or more difference. Whereas us with like, even if it was 100-degree water and the ice maybe minus 18, that's 120 degree difference. And probably in most cases, we're going to have something significantly less than that, just because the water cools and the outside of this bowl is going to be warmer than the inside of the bowl. So the difference within the cloud jar is probably only going to be like 50 or 60 degrees.
Would it work better if we like blew out the match and then put the wooden end, which isn't on fire, out on into the glass of boiling water and left it smoking and then put the glass on top?
Wow. Oh, like to get even more smoke?
Yeah.
Well, like I often say, the best answer to any question is an experiment. So I'd say try it. But I wouldn't, like, there's only so much cloud you're going to get in a jar as well. And it'll be limited both by the number of nucleation sites, like the amount of smoke you put in, but especially by the amount of vapor. So like usually from just one match and letting a fair bit of smoke go in, that's going to be more than enough nucleation sites. But in some cases, that might be what's limiting it. And then ways of getting more smoke would help. But like that's usually not what limits how much cloud you can make. Does anyone else have any other questions they want to ask? And someone had asked about upcoming sessions. Does anyone who's left want me to go over any of the things to expect in the next couple of weeks?
Yes, please.
Perfect. Okay, so on Tuesday, and it's on the schedule, but there's Jeff, who's the head of teacher programs at CERN. He's a really awesome and enthusiastic guy. So if you're not sure about attending that one, I'd say definitely, if nothing else, for like how engaging a speaker and how enthusiastic he is. It'll be an intro to CERN and the history of that part of particle physics. And CERN's the biggest particle physics lab in the world. So like, it's a good overview to what particle physics is. Next Saturday, it's very probably, and I just need to test out the experiments because my guest host canceled on me. So it's a couple experiments I was planning on doing anyways, but not next week already. Modeling electron microscopes and the Rutherford gold foil experiment. For both of those, it'll be trying to model how we can see something smaller than we can see with a regular microscope. And those experiments will be by dropping things of different size and seeing how good an image or shadow we can get of different objects and looking at the limitation in size. For that one,
like, how much would it be multiplied? How big will we see it?
Oh, we're not actually going to see anything bigger. Like like without a microscope, we're not going to do anything better than microscopes. But like the whole method of particle accelerators shooting particles at really high speeds at things, that doesn't.
For Christmas, I just got a microscope which can see up to 100 times, and I can attach it to Zoom. 1,000 times, sorry.
Oh, that's awesome. Maybe if you'd be keen to show something, I can work something in where we can start with regular microscopy and we can get to the limit for that.
Because I can attach it to Zoom and see from it and see anything.
That sounds great. Do you want to spend some time maybe near the beginning of next week's session where you'd be the guest host and you could show some things up close with your microscope?
Sure. Is there anything you want me to show in particular? Because I can do anything really.
If there's anything you think would be particularly interesting, like
the cool stuff I've found so far is like seeing like denim jeans, and you can see every little strand of material. You can see hair up close, and that's just freaky because it's like giant needles. And you can see cardboard, and it's like you see every tiny bit of it.
Those are excellent things to start with. And historically, the microscope was invented, or like the person credited with inventing and popularizing it, Anton van Leeuwenhoek. He was a fabric merchant, and he originally developed the microscope to look at the weave of fabrics. So like looking at denim jeans or any other fabric is very much in line with what the microscope was originally invented for. So yeah, that sounds great. We'll start off next week's session with you showing a couple things like that.
I'll be there for
Are
sure.
we starting at 6 p.m.?
Yes, it'll be starting at 6 p.m. And the like sign up form that'll be coming out probably tomorrow near the end of the day.
Okay, cool. See you next week. I won't be here on Tuesday.
Okay, so that sounds great.
I
See
also
you
won't be
next
there
week, and
on
I'm looking forward to having you share some stuff.
Bye.
Bye. And things have gone a bit late, so I'm probably not going to overview the rest of the schedule. I'll just mention there's a couple of guest ones on Tuesdays from Russia, from the Joint Institute of Nuclear Research. And 2 weeks from now, we'll be doing electromagnetics. So it's one where you'd want magnets and batteries for. And I'll send details for the equipment you'd want for that. Okay, on that note, thank you everyone who stuck around this long for the like extra questions or talking about upcoming sessions. I'm gonna let you guys go now. Have fun experimenting and have a great rest of the weekend.